Hi, my name is Uzair Nadeem.
Hi, I'm Vicaessee Paul.
I'm Clarence Wooten.
I'm Camacho.
And I'm Jonathan Warrior.
This experiment for using the third law, we're going to do the pick up the mass. So David here, which is 80 kilograms, is going to pick up a 9 kilogram book bag. So what's going to happen is, since he already exerts 80 kilograms of mass with the gravitational force on the ground, he's going to pick up the book bag with the amount of force that requires to lift 9 kilograms, and by doing that, it will also exert the same amount of force onto the ground itself. So as he picks up the book bag, the same amount of force will be exerted back on the ground, adding to his weight force added to the ground.
Alright, so for my experiment, Uzair, who has a mass of 81 kilograms, picks up his book bag, which has a mass of 9 kilograms. How much force does Uzair's feet exert on the ground while holding the bag, and how much force is the floor exerting on Uzair? So for the first part, we just used the equation force equals mass times acceleration. So we just added up both of the masses times the acceleration, and we got 882.9 newtons. And for the second part, using Newton's third law, which states that the magnitude of the first object must be equal to the magnitude of the second object. So that would just be the same force.
Today we're displaying Newton's third law by pulling a car. And the third law will demonstrate itself through the tension in the rope. You will see Clarence pulling this way, and then the tension in the rope will be pulling this way. And that is the force pulling opposite of where Clarence is pulling. Hence the term, for every action there's an equal and opposite reaction. Clarence, if you would care to do the experiment for us, please.
This is Jonathan, and I'm going to be explaining the forces behind the experiment of pulling the mass. In the recent demonstration, Clarence was seen pulling a car with a mass of 1,600 kilograms using a rope. He is moving at an acceleration of about 0.76 meters per second squared. The acceleration of gravity is 9.81 meters per second squared. And ignoring the friction and assuming Clarence is pulling horizontally, what is the tension of the rope? And as we can see here, tension is equal to the weight of the car plus the force of the rope being pulled. And as we know, Newton's third law is every force has an equal and opposite force. And as we can see here, tension is equal to the 1,600 kilograms, which is the mass of the car, times 9.81 meters per second, which is the acceleration of gravity, plus the mass of the car again, and the acceleration of Clarence moving at 0.76 meters per second. And if we were to multiply these two together, the mass of the car and acceleration of gravity, we'd have 15,696 newtons plus the mass and acceleration of the force of the rope pulled, which will give us 15,696 plus 1,216 newtons, which is a total of 16,912 newtons, and as the total tension of the rope pulled.
Equal and opposite reaction. And today we will show you here with two rolling chairs on a frictionless surface, or at least that is to be assumed. Now, David will push off of the back of Clarence's chair. And as you will be able to clearly see, they'll move apart equal distance because they both weigh the same from where David is applying the force to the chair. Clarence will move forward a certain distance, and David will move back the same distance. Now, David, if you please do the experiment. That's a wrap. That we experimented on with David and Clarence pushing each other in the rolling chairs, we will now do on the board mathematically. Problem states, David and Clarence have similar masses of 81.6 kilograms. On a frictionless plane, it should have said on a frictionless horizontal plane. I feel like rewriting it. On a frictionless horizontal plane, if David pushes Clarence from a standstill with a force of 5 newtons, how much force is exerted on David? Now, as you can see by Newton's third law, we can observe that force equals force. Same thing as force equals mass times acceleration. Mass times acceleration is just a different way of writing force out. Now, we can see here that acceleration is dependent on mass. So we don't need to know the acceleration in this problem to find out the answer. And we can also see right here, so if mass 1 is similar to mass 2, then force 1 is also similar to force 2. So we get 5 newtons is equal to 5 newtons. 5 newtons is how much force was exerted on David when he exerted the force on Clarence.